This is the 2018 Calculus BC Frq number 6. So we are given a Maclaurin series for ln of 1 plus x. So let me write this here. Yikesies, that's ugly. Okay, and they want the Maclaurin series for f of x. So we're going to go one step at a time. We don't want x, we want x over 3. So we're going to use the composition. We're replacing x with x over 3. So we do that in each term. Now they want the first 4, so there's 4 terms, and the general term. So in the general term, we're going to replace the x with x over 3. Plus dot dot dot. Now I'm going to rewrite this. So we're going to end up with x squared over 3 squared times 2, x cubed over 3 cubed times 3, that's a minus, x to the 4th over 4 squared, no, 3 to the 4th, excuse me, times 4 plus dot 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 negative 1 and plus 1 x to the n over 3 to the n plus dot dot dot. Okay, we're almost done. So that was the composition, and then we're going to multiply by x. So if you can multiply this function by x, you just multiply each term on the right by x. So we'll have x squared over 3, x cubed over 3 squared times 2, x to the 4th, x to the 5th, and then what's going to happen to your general term? You're going to have an extra x, so it's n plus 1 over 3 to the n plus dot dot dot. So that's part A, and we're done with that. Now we're going to move on to part B. And they're asking the interval of convergence. So for the interval of convergence, we're going to use the ratio test. Why the ratio test? Well, if you see, we have x's to powers, constants to powers, so the ratio test works well there. So let's do this. Our r is going to be the limit as n goes to infinity. So we are going to get the n plus 1 term. So all these are going to have n plus 1 added to them. So we're going to have negative 1 to the n plus 2, x to the n plus 2 over 3 to the n plus 1 times n plus 1 times, now we're actually dividing by this, which is multiplying by the reciprocal. So we're going to flip that over and multiply. It's absolute convergence, so that's what we're testing for. Now, some nice things, you could ignore these because of the absolute value. And if you look, you have 1 extra x on top. So when you cancel those out, you're left with x. And then with the 3's, You have n of them there, you have n plus 1, so there's an extra 3 on the bottom. So when you cancel those out, you're left with the 3. So what are we left with? On top, I see just an n and an x. On the bottom, I see a 3 and an n plus 1. Now, I'm allowed to pull out the x and the 3. Why? Because those are constants. And you have to understand why they're constants. What's changing? N is changing. So why is x a constant? Basically, if you put a value of x here, that x is fixed, and that x is fixed. It's not changing. It is a constant. So therefore, we consider that a constant. This limit here is 1. So therefore, our r, absolute value of r, is x over 3. Now, we know for the ratio test, this function converges. Well, I'm going to run out of room here. It converges when the absolute value of x over 3 is less than 1. So I'm going to multiply both sides by 3. Absolute value of x is less than 3. And getting rid of the absolute value, it converges over or between -3 and 3. But with the ratio test, when r equals 1, it's inconclusive. What value makes 1? +3 and -3. So we need to test those points also. So what happens when x equals -3? What's going to happen? I'm going to put a -3 right there. Okay, so that's going to get me -1 to the n plus 1, -3 to the n plus 1 over 3 to the n. Now what's nice about this, these have the same exponent, so I can combine them together. That gives me 3 to the n plus 1 over 3 to the n, so I have the summation. And if I keep going, so the top I can rewrite as 3 to the n times 3. So these are going to cancel. So I get 3 over n, which is 3, 1 over n, and that's a divergent harmonic. Now I'm going to plug in +3 to test the other point. So we diverges at -3. What happens at +3? Well, we're going to get something very similar. The only difference is it's going to be a +3 there. And we're going to run through a similar scenario. But instead, we're going to get -3 to the n plus 1. But that top will simplify to -3 to the n and a -3. And so what's going to happen, these are going to combine under 1. It's going to be -1 to the n. I forgot my summation. You're going to get -1 to the n times -3 over n. And again, why? Because 3 to the n and -3 to the n go under 1n, and that'll be -1 to the n. Okay, so I conclude this is an alternating series, and the terms decrease in magnitude to 0, therefore converges. Now you could also have done this, factor out the -3 in front, and say this is an alternating harmonic series, therefore it converges. Therefore, our final conclusion, the interval of convergence will be from -3 to 3, but it converges at 3, diverges at -3, so we want it equals there. So there is our interval of convergence. Just to point out, we know it converges between these points. So that's my language there. Converges when this is true, but it's not the interval of convergence here. I need to check the endpoints. Then I have the interval of convergence. All right. Part C, P4 is a fourth degree Taylor polynomial. Using the alternating series error bound, use the alternating series error bound to find an upper bound for, and this is the actual value, this is the approximated, so you subtract that, that's the error. So we know that error is less than or equal to the next unused term, which will be the fifth degree term. But in order to use this error bound, we need to conclude a couple of things. This needs to be an alternating series decreasing in magnitude, where the terms are decreasing in magnitude to 0. Well, we've already, well, I guess we haven't determined that. So you can ignore, excuse me, you're allowed to ignore the negative sign because we're looking only at the magnitude. Okay, this is alternating, so we know it's alternating. And it is decreasing in magnitude if you look at the terms. All right, because the denominator keeps getting bigger and bigger and bigger, so it is decreasing in magnitude. So we should say how should I state this? The Taylor polynomial I am just fumbling here. The Taylor polynomial, I don't even know how to write anymore. Poly. I know how to write poly. Polynomial is an alternating series whose terms decrease in magnitude to 0. Therefore, what is the error? It's the next unused term. Well, what is our next term? We have it already. It's right here. I'm going to copy and paste this. Let me lower all this, give us more room. And it's going to be absolute value. But what is x? It is 2. So that's 2 to the 5th over 3 to the 4th times 4. And we would stop there. You could simplify, but why? You could say that cancels out 2 of those, leaving 3. So you could say this is 8 over 3 to the 4th, which is 8 over 81. That would be foolish to go that far, but that is the answer. Also, I want to make a little side note. Going back to part B, we did the ratio test. Now, you could actually have made this much shorter if you noted a couple things. So this ln comes from this series. And then you replace x with minus x, and then you get 1 over 1 plus x, and you have the series for that. Then you integrate it and you end up with ln. So the thing to point out, we know this converges when absolute value of x is less than 1. We know that. And then when you replace x with minus x to get 1 plus x, it still has the same radius of convergence. Okay? And then when you integrate it, it still has the same radius of convergence. And then when you replace x with x over 3, you can put an x over 3 here, and that will be the radius of convergence. And multiplying by x doesn't change anything, so you could actually have gone directly to this, explaining how you get that. Okay, that's the radius of convergence for that function. Then you wouldn't have had to do all that ratio test. But I just want to point that out also.